Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries. I am super excited for day 11 of our hashtag 30 Days of Code challenge with Educative. Let's get into this problem. Today we're breaking down a classic matrix manipulation problem called set matrix zeros. This is one of those problems where the idea sounds simple, but the moment you try to do it in place, things get messy, fast. So we're going to walk through the intuition, the naive mistakes, the correct beginner approach, and then step-by-step build our way up to the optimized in-place solution used in top interviews. Here's the challenge. You are given an M by N matrix. If any cell contains a 0, you must set that cell's entire row and entire column to 0. You must modify the matrix in place, and the optimal solution uses constant extra space. That means no extra arrays proportional to the size of the matrix. On the surface, this feels straightforward, but once you start modifying the matrix, you will notice that the zeros begin to spread in ways you do not intend. So, the real challenge is preventing your own updates from corrupting the final answer. Let's start with a visual example. Look at the left matrix. The only 0 is in the middle. That one 0 forces the entire row and the entire column to become 0. So the final output matrix has an entire row of zeros and an entire column of zeros. Very direct and very easy to see with your eyes. But here's an edge case you need to recognize early. If the first row or the first column contains a 0, that entire row or column must also become 0. This matters later when we talk about optimization because the first row and first column play a special role in the in-place version of this algorithm. This is the moment every beginner has the exact same idea. Scan the matrix. Whenever you find a 0, immediately turn the whole row and column into 0. Then keep scanning. And the problem? Here's what happens. Say you find a 0 at position 1, 1. You immediately zero out row 1 and column 1. Now, when you scan position 1, 3, you see a 0 you just created. So you zero out column 3, which shouldn't be zeroed. The corruption here spreads. You cannot tell which 0 belonged to the original matrix and which zeros you added. This is why this naive idea fails. The first correct solution most people arrive at looks like this. Instead of modifying the matrix immediately, you use two helper arrays. One array marks which rows should eventually become 0. The other array marks which columns should become 0. So we do a first pass to record where zeros originally exist, and a second pass to apply the changes. This prevents the ripple effect because you never modify your source data during the recording stage. This is the Python code for the two-array approach. We create arrays for rows and columns. We scan once to record. We scan again to apply zeroing wherever needed. It works. It is clean. It avoids the corruption problem. But it uses extra memory proportional to the number of rows and columns. This is allowed, but it's not optimal. The time complexity of this approach is O of M times N. You scan through the matrix twice. That part is already optimal because every solution must at least look at every cell once. Space complexity here, though, is O of M plus N. For small matrices, this does not matter, but interviewers love to ask, can you remove the extra memory? This is where many interviews take a turn. Your code works, but they challenge you. Can you do this fully in place? Can you avoid those extra arrays? Can you solve the ripple effect problem without needing extra row and column storage? This is your cue to reach the optimized constant space version. Here is the breakthrough. Instead of using separate arrays, use the first row and the first column of the matrix itself as your marker arrays. Whenever you see a 0 at position R, C, mark it by writing a 0 into matrix position R, 0, the first cell of that row, and matrix position 0, C, the first cell of that column. These become your markers. The first row and first column now store all the information you need. Since these markers are stored inside the matrix, you do not need extra memory. The only memory that you store are two small booleans to track whether the first row or the first column originally contained a 0. This idea gives you constant space. The optimized solution happens in 3 passes. Pass 1. First, we check if the first row or first column originally contains any zeros. Store that in 2 Boolean flags. Then, scan the rest of the matrix. Whenever you find a 0 at position R, C, mark matrix of position R, 0 and matrix of position 0, C as 0. Pass 2. Use those markers to zero out the appropriate cells in the interior of the matrix. Skip the first row and first column for now. And pass 3. Finally, use your 2 Boolean flags to zero out the first row and first column if needed. 3 clean phases, no corruption, and no extra arrays gives you constant space here. Here's the full Python code for the optimized solution. Notice how we scan the interior of the matrix, starting from row 1 and column 1, leaving the first row and first column for the final pass. Those 2 Boolean flags let us safely reconstruct the true state of the first row and column at the end. This is the version that interviewers love. Time complexity stays the same. You still have to scan each cell, so it is still order m times n, but the space complexity is now constant. There are no extra arrays, just 2 Boolean values. This is the best possible version of the algorithm. This approach is elegant because it is minimal. It does the job without over-allocating memory. It satisfies the constraints perfectly, and it demonstrates that you understand how to think about propagation, side effects, and in-place mutations. This is the type of solution that gets coded during real interviews by strong candidates. Set matrix zeros teaches you several important algorithmic skills. How to prevent unintended propagation of changes when modifying data in place. How to keep track of the original state while transforming a structure. How to use existing memory as markers instead of creating extra tools. And how to refine a correct but expensive solution into an elegant optimized one. And that's a wrap for day 11. If you liked this video, like it down below, share it with a friend, and also subscribe to our channel. We would love to see you and have you here again. We will see you next time. Bye.